So it's a good color for Venn diagrams. I'll blue. I used to see that little. There we go. Venn diagrams. So Venn diagrams. I think we've all heard of Venn diagrams, right? Those are the things that are like, you know, you can have one circle here and one circle here, and this is like actors in Ocean's 11, and this is actors in The Bourne Identity, and then Matt Damon would be here in the center. But the point is, this is a Venn diagram, right, where you can see the ways two sets play together, right? You can see how they intersect and things like that. So let's talk about the options. The options for A is a subset of B. So if A is a subset of B, the Venn diagrams can look like this. And in fact, I'm going to go ahead and make this A and green B. So if A is a subset of B, that means we're going to have B, which is some, like this is the visualization of the set B. Maybe I'll write it here, actually. This is B. And then A is going to be some set inside of it, right? B is the big set, A is the set inside of it. And so this right here, this is the option where A is what kind of subset of B? Any guesses? Proper. So all the time. Proper, right? A is a proper subset of B because you can see clearly here that B is bigger than A. There's like some elements out here. So B is bigger than A because B contains elements, or bigger than the right word. B contains elements that aren't in A. So A is a proper subset of B. It really is. It's not the whole thing. It's a subset. But the other option would look like this, where you have A actually equals B. And so that's when you have B right here as some set, but then A is just right on top of it. Here, B and A are the exact same set. B and A is just like DNA. The point is, these are your two options for being a subset, right? Either you're a proper subset or you're not a proper subset. If you're not a proper subset, that means you're a subset, but also there's no element in B that's not an A. So that means it contains the whole thing. That makes sense? And the more interesting one is options for A not contained in B. So if A is not contained in B, what's one way that A and B could interact but not have A contained in B?
B is smaller?
Yeah, that would totally work, right? That's a good one. So if this is B, but A is even bigger, well, then this is our option that here, I'll write on the bottom. Here we're looking at B is a proper subset of A. If B is a proper subset of A, well, then clearly A is not a proper subset of B, right? You can't fit A inside of B. Yeah. The reason being, if we were a proper subset, by definition, what that means is that there exists an element of A not in B. So by definition of being a proper subset, there's going to exist an element A here, not in B. But if this element of A is not in B, that's exactly what it means for A to not be contained in B. There exists an element A not in B. Element of A not in B. What's another way? Or is it the only way? Why not the classic Venn diagram, right? Why not have B here and A here? So here, B is certainly not contained in A, and A is certainly not contained in B. Right? Doesn't go either way.
Wait, so the size doesn't matter as long it's like the positioning of it, or
Well, exactly, right? So for example, the set pi, e, and 5 is not contained in A. Because pi and e are not natural numbers. So this set right here is not a subset of N. It's not a sub-collection of N. So it's not about size. It's about in and out. In this case, A, if we draw it like this, like if this was A right here, and this was B, the natural numbers would be this giant kind of set that contains all the natural numbers. And then A would be this very little set. And 5 happens to be in both A and N. So 5 would be in the intersection. So they intersect in one place. But clearly, this set's not a subset of B. A is not a subset of B here because pi and E aren't in N. It's not a collection of N. Right? A subset of N would be any set of natural numbers. Right? Any set made from N itself. We don't have that here. Does that make sense? You good, Toro?
yeah, that makes sense.
Perfect. There's one more way that these sets can interact. And I guess I should also say here, we'll define what this means tomorrow or Thursday. So what this means is that A intersect B is not the empty set. And that just means that there is an intersection here. And that totally gives it away. Because that means the other option is just imagine if you had, they're getting smaller as we go because they keep running out of room. Imagine if you had this. Right, where this is A, this is B. And clearly here, B is not a subset of A, and A is not a subset of B. But more importantly, A intersect B is the empty set, which means there's just no intersections between A and B. Nothing's in both A and B at the same time. So these are the 3 ways that A cannot be in B, A cannot be contained in B. These are the 3 ways A can be contained in B, or the 2 ways A can be contained in B. And these are just interesting things to think about. They'll be very useful when we start proving weird theorems about intersections and unions and things like that. But anyway, we'll do that Thursday. Before we leave today, any questions on this, by the way? It's all a race, so I hope not.